Okay, so we have the new booklet, wave particle duality and spectra. Key areas you need to know listed in the front as usual, and you can use these when you're revising this booklet to ensure that you've covered all the bases. To start with though, we're going to look at an experiment called the photoelectric effect. In 1887 it was discovered that radio waves, when observed in an experiment, were creating sparks that were much bigger when the light from the transmitter was allowed to fall on receiving spheres. That doesn't mean much to you guys just now, but we've got a video we'll watch in a minute. So basically he sent radio waves across the air in the room, and sparks were experienced between two metal spheres. If you imagine the Van de Graaff, when I hold one of the metal spheres close to the other one, you see the sparks jump. Similar sort of image would have been what Heinrich Hertz observed. What he had discovered was called the photoelectric effect. This effect was first explained by Einstein, and he subsequently won a Nobel Prize in physics for it. So if you have a transmitter and a receiver and you send radio waves between them, you will notice sometimes that little sparks appear between them. Under certain situations, an electrically charged object can be made to discharge by shining radiation at it. What this would mean is you've charged up some sort of metal object and you take a UV lamp and shine it, and you see electrons moving in the form of sparks. We can charge a device and we can measure how much charge we've put on it, how many electrons we've stored on it with a coulometer. What we've got in school is called a gold leaf electroscope. A charge is added to gold leaf electroscope with a thin piece of gold, will then rise up at an angle from the vertical rod which is attracted to. So you use the coulometer to measure how much charge you put onto the leaf. The leaf is then attracted to the metal plate. We do have this experiment. I'm going to let you watch a video of it today, and tomorrow we'll do the live one in class because there's so many of you absent today. Different frequencies of electromagnetic radiation can be directed at different types of charged metals. The metals can be charged positively or negatively. What we should observe happen is that if we have visible light incoming to the metal plate when it's negatively charged, nothing happens. If we have visible light incoming to the plate when it's positively charged, nothing happens. If we have UV light when the plate is positively charged, nothing happens. However, if we charge the plate negatively and we have UV light, this gold leaf would fall back down to where it is at rest. So to make this a bit clearer before we actually do the experiment tomorrow, let's go to the National Science Centre for a little explanation, and then we'll have a look at it.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now let me show you that again. I've got a perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on, and it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
So we'll have a chance to carry out this experiment when we've got everybody back tomorrow, but we can talk about the theory just now, and I'm sure over it tomorrow as well. So if you have negatively charged plate and the gold leaf, okay, hasn't moved, it's still stuck at an angle. What you've got is electrons stuck on the top of the plate and then electrons, so negative charge all the way down the rod. UV light is shined on this, and UV light, because it's a higher frequency, than visible light, causes the gold leaf to discharge. So it must be freeing these electrons on top of the plate and the rod, and this effect is called the photoelectric effect. It's the ejection of electrons from a metal surface when it's exposed to radiation. So if you think about it, something happens when the UV light enters the plate. Okay, it comes down here. Your photons of light hit the electrons and give them enough energy to leave where they're being held. We will go over this in a bit more detail tomorrow when we've got the experiment out on the desk. If a metal surface is irradiated with light, it depends what type of surface it is. It will not happen with brass. Another factor is the effect and which type of light. Visible light doesn't have any effect. Ultraviolet does have an effect because ultraviolet has a higher frequency, which means more energy. The effect is not produced by ionization of the air, since only the negative plate discharges. If it was ionization, you would see something happen with the positive plate as well, because you'd have electrons being freed and atoms changing. So this is the bit we're interested in. How do we explain what's happening? If you think of the term quantum theory, probably not much comes to mind at the moment unless it's something you're interested in, because it's not something we talk about in school. How do we explain why radiation from something that is glowing changes in colour from red to orange and finally to blue or to white hot? If we assume that energy exists in individual units, and we call that a quanta, rather than as a wave, that's when you can start getting closer to understanding what happens with light. Einstein took this idea of quanta, packets of energy, and decided that if we consider the photoelectric effect where light falls on a plate and releases electrons from the metal that have specific energies, what we can do is describe a beam of light as tiny bundles of energy called photons. So how much energy does a photon have is proportional to its frequency. The energy of a photon E is directly proportional to the frequency f multiplied by Planck's constant h. This value, 6.63 times 10 to the negative 34, will be given to you in the data sheet that you get in a test. This image explains what's happening. Electrons are held on the surface of the metal. Incoming photons hit the electrons and give them enough energy to be released from the metal. So let's just pause for a second.